First, we'll hear from Dr. Jason Clyburne, who is a professor, of course, in environmental science and also in chemistry. He's also an adjunct professor at Simon Fraser University and holds a Canada Research Chair, Tier 2 Environmental Studies and Materials. He has his PhD from Dalhousie University. In 2013, he was the recipient of the St. Mary's University President's Award for Excellence in Research. His research deals primarily with inorganic and organic materials as they apply to green chemistry. So his research interests include solids and liquids for reversible gas absorptions. By the way, if one of the qualifications of the host of this was their knowledge of chemistry, there'd be somebody else standing there right now. So I'm sort of, I may fake that I know what these terms mean, but I really have no clue. Ionic liquids, polymers, and gels for separations, synthetic main group chemistry, and chemistry of the hydrogen atom. His work has been published in journals such as Inorganic Chemistry, Marine Pollution Bulletin, Chemical Communications, Main Group Chemistry, and Organic and Biomolecular Chemistry, among others.
Thank you. It's nice to be here. I like birthday parties. I've seen a few of them myself. But it's a big one for ENVS, and it's great to be part of it. It's always nice to get out of our teenager years. They were rough, but now we're mature. So I'm going to talk to you about some of the material that we've been working on in our lab and as part of our Center for Green Chemistry. So as you heard earlier, our research is broad. We focus on fundamental chemistry, and we also do chemistry that does stuff. And that mostly focuses on the gases and liquids for gas absorption and separations. Just to begin with, I always thank the people who give money. Of course, St. Mary's, NCANA, NSERC, Environment Canada, various other funding groups here, most notably Cougar over at Ventures Institute, and the Center for Oil Sands Innovation. But it all comes down to people. And people are is the currency of the university. These are the people that have gone on and have worked on the work that I'm going to show you here today. Katie Nizio began the work, Cody Sheriff, Alex Murphy, McPherson, Naomi, Courtney, Luke, Graham, Jason. Of course, I'd like to thank Kathy Robertson, who looks after the lab and most issues. So, green chemistry, just by way of introduction, it's the set of principles that make us focus on doing various important industrial processes as cleanly and as greenly as we can. And some of these processes are in fact quite black, as you'll see today. But we try to make them better as we go along. One of the things that I'll talk to you today will be definitely black. So here is the pollution prevention hierarchy. We want to make the biggest impact on pollution prevention. We work right at the beginning and prevent the production of waste early on. Then if we do produce something that's wasteful, we try to reduce our footprint by recycling or reusing that material. Then we want to look at treatment and disposal. These here are basically recognition that you failed to do the top jobs. Okay? If you don't look at preventing and reducing, you're down to treatment. This is the way chemistry used to be done. This is the way waste management was done. It was focusing here, not focusing at the top. In Canada, we have some grand challenges. Number one, in my opinion, would be carbon dioxide management. The next one, very close behind and linked intimately, sort of joined at the hip, is bitumen processing. Of course, it comes down to oil spill management. We also need to look at efficiency, green or resource extraction. There's, locally, we have farm and aquaculture issues, pesticides, various metals in the environment, organics, although this is slowly getting more and more controlled, and of course pharmaceuticals and waste. Now I was going to talk to you today mostly about carbon dioxide capture, but I'm not going to. We've published a number of papers in this area, and there's been various bits of press on that. I'm not really going to spend too much time on it, because I'm going to talk about something else. But we've looked at making various complexes of carbon dioxide and binding them into a phase at atmospheric pressure, which is where this process has to occur, and then release the carbon dioxide in more energy efficient and economical routes. Now, this is the way that carbon dioxide capture is looking, and it looks like it's going to be developing here within Canada. Most environmental groups incorporate carbon capture in all models for low carbon futures. This includes the David Suzuki Foundation. You look at the various reports. So carbon capture is really going to be used in the future if renewables don't come online fast enough, and that appears that is going to face certain challenges. And the reason is the low price of oil. And that's what I'm going to talk to you about today, because this is something that's going to be on people's minds for the next little while, is understanding bitumen. I went into the environmental science course in October when the price of oil dipped down below $60 a barrel. And in my opinion, that has changed the landscape of Canada and North America in a more revolutionary and in a faster way than any changes that I've experienced in my life. And the low price of oil is hitting the government, it's hitting our budgets, it's hitting everybody in this country. And it comes down to the understanding of bitumen. And I'm going to talk to you about some material that we're going to be publishing very soon, because we've just finished it up. And oil is one of those things that really people don't like, because it produces carbon dioxide when it's burned, the emissions go out. And we're always fearful of the increased carbon dioxide emissions, but we also should be concerned with the handling of this oil. And when an oil spill occurs, it can be on land or on water. And on land, fortunately, those are a little bit easier to handle because you can literally scoop up the material. But when an oil spill occurs on water, the challenges are much, much greater. Now oil, regular oil, like West Texas crude or light oil from the Middle East, it floats on water. It's easy to clean up. And I'll show you how that's done in a minute. But what happens is that the oil is not compatible with the water. And what happens is that you get this big slick floating on the top. And when that big slick floats on the top of the water, you get creatures like ducks and birds and seals interacting with the slick, and they die. So the safest thing is to disperse it. We haven't got a snowball's chance in someplace hot to clean it up. When you look at the results for oil cleanups off the surface, they're typically on the order of 10%. So what we do is we disperse it using oil dispersants. Now these oil dispersants work pretty well. I'll show you what. This is in salt water. This is my former student Tom King. We have an oil blob here. And what we're going to do is we're going to spray a little bit of Corexit, which is the standard oil dispersant. This is light oil, and it disperses very quickly. Very, very quickly. And then, this is just another experiment we showed where we just put it in one spot, and it does not disperse quite as well. So if you overspray an oil spill, you get very effective dispersion. If you control the dispersant, you don't get effective dispersion. But bitumen, the stuff that you read about in the newspaper all the time, is diabolically more complex. It's thick oil, this heavy oil that we isolate in Alberta. It's mined off the surface. It's thick and it's tar-like. It can be refined into more valuable products. By that I mean lighter oil, the stuff that we burn in the car. But it must be diluted for pipeline transport. And you're going to see a little bit more of why this has to be done. And it's shipped by rail, or pipeline, or by ship over fresh and ocean waters. Alberta is captive. And this is where that bitumen is. And right now you're seeing a test of wills of people in politics, people using green arguments to prevent the development of pipeline and transports within the country. But it's coming down not to those issues, but raw politics. And if this bitumen is going to be shipped, it's going to be shipped to 3 places. Either to the west coast, off to the east coast, or down to Texas. Now, this is going to be a shipping-only option. So there's no refineries out here. So this will be a shipping-only. But if this material goes this way or this way, the material will be refined in North America. Now, with the development of these pipelines and shipping comes the risk of spills. And unfortunately, we don't have anything that will clean up a bitumen spill. Nothing. There's nothing in the toolkit. If you put Corexit or any of the other dispersants on bitumen, it doesn't do anything. It looks at it and laughs. And the reason is that bitumen contains 20% of a material called asphaltenes. Okay? That's the stuff that they use to make the roads and asphalt, whatever you want to call it, asphalt. And this material in the oil, or the bitumen, is what causes it to cake. It solidifies, and you can't disperse it at all. Bitumen, or Alberta bitumen, is sort of like a Beaujolais Nouveau. It hasn't sat in the ground long enough to break down into small pieces. It's tar, and it's thick. And it's this component that prevents it from being dispersed. The Friends of the Earth have already put out a lot of issues, a lot of commentary on this, because a bitumen spill is more diabolical. It doesn't float on water. It sinks to the bottom. And that is the worst place for it to go, because there's long-term implications. It's not like a big dose of oil and then the ecosystem recovers slowly. What happens is, it's a slow poison. So, in order to disperse this bitumen, you would think that we could go to a toolkit to do this. But there's nothing there. And you go down, you look at what we can do to a bitumen spill, there is simply nothing. When it comes to industry right now and you get an oil spill with bitumen, the best you can do is hope that it's cold and it solidifies. Okay? So what happens with fresh water and salt water is the bitumen will go in, float for about a day, and then sink to the bottom. What we need to make is a PFD, a petroleum flotation device. Now, one of the things that really struck me a few years ago when I was traveling across the United States was all the waste biomass just sitting on the side of the road. And one of the biggest waste products was actually hay. It's an interesting material. It's hydrophilic. It likes water. It breaks down quickly. And it will float for a while. The problem is that waste materials like that do not want to be with oil. They don't stick. It doesn't stick at all. It's like when you make pizza dough, right? You have the pizza dough sitting there. It's all full of carbohydrates. It likes water, but not the olive oil that you put on the top. It doesn't mix in, it stays on the top. So what we did was we said, how can we convert this cheap, widely available biomass into something that we can use to make a flotation device? And what we did was really, really simple. What we did was we charred the hay. And basically, you take a Bunsen burner, burn the hay in the absence of oxygen, so it doesn't burn, but it chars, like charcoal. And then, once you do that, you can characterize it, and then you can also coat it with calcium oxide, which is like from burned bones and things like that. Again, another waste product, or from calcium carbonate cooking. And it works really well. The surface of this material, this charred straw, really loves oil. But the measurement is not the ability of sticking to oil, it's actually the repulsion of water. So this is regular hay. You put a drop of water and you measure this angle here, it's called a contact angle, and it interacts strongly with the surface. But once you char it, you see that the water still beads. The water beads up, and this is a very strong contact angle. So uncharred hay loves water, and charred hay doesn't like water. And it works. It works beautifully. A little bit of base on there, the calcium oxide, it makes a soap in situ. It sticks to the straw and it floats the bitumen for like over 4 days, reliably and safely, allowing you a chance to either wave action to disperse it, or if you can catch it, you can burn it, or you can burn it in situ. Or, the most exciting thing is to apply it prophylactically along a coastline, and then that will prevent the bitumen from coming in and getting on the rocks, where you haven't got a chance of removing it, but with the straw there, the hay there, it will interact with the material, and then you can clean it up a little easier. So there are significant implications. This is the first development of a tool to go into the toolkit for cleaning up bitumen. And we're going to be publishing this very soon. I turn my attention back to writing. But I'd like to thank you all for coming. I know that this is a little bit unusual, a little bit of black with the green, but thank you, and thank you for your support through the years. Thanks. That's the way I see it. You can make it, it's dirt cheap, right? It's easy to make, that's the beauty of it. And you can either spray it from a boat or drop it from a helicopter. I don't know if you've ever been around a forest fire, but you drop it. And that's really the only way you could do it. It's low tech. It's absolutely low tech. And that's why I think people are interested. Yeah. There's lots of ways. Straw, all you need. One of the problems with Nova Scotia, I don't know if you were raised on a farm, but I was raised on a farm. So what happens in July? You get a rain on your hay. You get thousands of bales that are molded. That's all waste. You can't do anything with it. Maybe you can spray it on to your blueberries to burn instead of, using a fuel. You know what I mean, right? Yeah. So there is thousands of bales of hay that are wasted. And that's something you can do with it. Now we just let it rot, right? Or turn it into biomass fuel for someone's pellet stove. You have to prepare it before. You'd have to have just like most places, most harbors have a toolkit for oil spills, like the booms and the dispersers. This would be another one where you just have to have, 100 tons of material sealed up, ready to go. It's, what really amazed me when I saw it is people talk about putting kitty litter to soak up oil, right? That's insane. They don't know chemistry. Because kitty litter is what? Rock. Oil is oil. Are they going to interact? No. It's like, you see that in the internet, you go do some chemistry, go learn how it works. But this would. This would. Oh, and char the bed sheet, because you need to make it. The bed sheet it likes water, right? You're a hot summer night and your bed is sticky and gross. Well, that's because it likes the water, right? So you're going to need something that doesn't like water. So you'd have to either char the bed sheet or make one out of plastic. That would be the hope. It's charred, right? So as long as you've already oxidized most of it, right? Because it's going to be graphite on the surface.
So you can prepare a lot
Yeah.
and store it.
In a bed.
That's not a bad idea.
In a bed. It is highly active charcoal. is what it would be. Made from something that's waste. And flows. As biomemory. With bad stuff stuck to the outside. Any other questions? Thanks again.